All right, guys, so in this problem, we've got an 850 Newton box, so that's the weight of the box, sliding down a 50-degree inclined plane, and the box is accelerating. So it's an 850 Newton box. It's at a 50-degree incline, and it's accelerating at 2.5 meters per second square down the plane. And what they want us to find is they want us to find the parallel and perpendicular components of the weight. They want us to find the net force, the frictional force, and the coefficient of friction. So it's asking for a lot of stuff. So the first thing we're going to do is go over to a new slide here and see what we can do with this problem. A picture is worth 1,000 words in physics. So here's our inclined plane. Our angle is 50 degrees. We've got our box up here on our plane. Whenever we're working with an inclined plane, the first thing we want to do is go up to that box, go to the center, and what are we drawing first? The weight, straight down. Weight acts straight down. So let's make that be the weight. And then we're going to take that weight and break it into what two components? One perpendicular to the inclined plane and one parallel to the inclined plane. And we do that like this. That one's going straight into the plane, so that this angle right here is 90 degrees. This one, we're going to draw in like that, so I'm going to shorten that line a little bit. Oops. So now we have F parallel and F perpendicular. We also need to remember that this angle is always the same as that angle right there. We also need to remember that this black line represents what? That's the weight. And we know the weight in this problem. It's 850 newtons. So the first part of this question was to find the components. So to find those components, we're first of all going to find this parallel component, and we need to say sine. So we're going to say the sine of our angle right here, which is 50, equals opposite over hypotenuse. So our parallel component of our weight is equal to the sine of 50 times 850. And that is about 651. I'm going to carry out a couple of extra digits for a minute, but 651 would be our answer if we were writing it down now. I'll carry out a couple of extra digits for the time being. And remember, that's down the plane, right? That's pushing the box down the hill. The perpendicular component, we'll find the same way, so we'll use cosine. We're looking for this side right here. Cosine 50 equals F perpendicular over the weight, 850. So the perpendicular component of the weight is going to be the cosine of 50 times 850. Which is going to give us 546 if we were writing down the answer now. Carry out a couple of extra digits though, like so. Now remember, the parallel component of the weight is pushing the box down the hill. What's the perpendicular component doing? Into the plane. And what's the reaction force to that always going to be? Perpendicular component into the plane, what pushes out of the plane? That's the normal force, right? So in terms of magnitude, that is your normal force. It's the reaction force to that. All right, so we got the components. The next thing the problem asked us to find was the net force. Well, that's easy enough to do. It gave us A, it gave us M. Or sort of gave us M, right? It gave us the weight. We know weight is mass times gravity. So in this case, we're going to take our weight, 850, divided by gravity, 9.8. The mass in this problem is 86.73. So to find the net force, take the mass times the acceleration. The acceleration was given to us as 2.5 down the plane. So we'll take our mass, 86.73, times 2.5. So our net force, 216.84. And again, if we were writing down our answer right now, we'd say 217 to get the sig figs right. And that net force, the box is sliding down the plane, so we ought to put an arrow to let us know which way. Everybody with me so far? All right, now the friction force, this is where it gets a little tricky if you're not thinking about what's going on. We have a parallel component of the weight that's pushing us that way. And it's pushing with a force of 651 newtons. But it seems like the box is only getting pushed how hard? 216.84. Where does that other 400 and something newtons go? It's canceled out by friction. So what I'm hoping that you see is, think of this in terms of an equation. In this equation, our net force would be equal to what? How can we write what I just said in an equation? F parallel minus FF, right? You guys with me on that? That the net force is caused by the parallel force pushing down and the friction pushing up. And if we subtract those two, that should give us our net force, which was 216. Well, in this case, we want to find the frictional force. So let's just solve that for FF. Do a little algebra. And if we did the algebra on that, let's see, I would add that to both sides. And then subtract F net. So FF would be equal to F parallel minus F net. Everybody okay on my algebra there? So in this problem, we've got a parallel component of 651.14. So let's go 651.14 minus our net force was 216.84. So we end up with a force of friction of 434. And that's acting which way? Remember, force is a vector, so let's put an arrow like that. Or just say up the plane would be okay. There's one other piece of this we have to do, and that's the coefficient. And I'm going to have to make a little space for that. So I'm going to do some erasing up here. So to find the coefficient of friction, we know that's where we go to our fun equation. Solve that for mu. Now in this particular problem, we already know the frictional force. We just found it, 434. What's the normal force? It's equal and opposite to the perpendicular component of the weight. So it's the 546.37. The newtons cancel. Coefficient doesn't have any units. So we divide that out. 434 divided by 546.37. So we end up with a coefficient here with 3 sig figs, which is what we need, of 0.794. Everybody okay with that? All right, let's do one more of these. So help everybody on the next quiz. So in this one, a similar kind of problem. This time we've got a 20 kilogram box. And it's sliding down a hill again. This time the hill is at a 40-degree angle. And it's got an acceleration of 0.5 down the plane. And what we want to know is the friction force and the coefficient of friction. So, again, go to a new slide. Draw it. Again, our angle in this one is 40. We'll put our box up here. We know the mass of the box is 20. We know the acceleration of the box is 0.5. It's down this way. And that's all we know. What we're looking for is the force of friction and mu. So as always, first thing we're going to do is we're going to come to the center of our box. We're going to draw a line straight down, and that always represents what? Weight. We need to calculate the weight. 20 times 9.8 is going to give us what? 196. That's the weight, 20 times 9.8. So this red line is 196 newtons. We're going to break that weight into two components. One perpendicular to the plane, one parallel to the plane. Remembering that if this angle is 40, that's also 40. So we need to find these two components, F parallel, F perpendicular. And we'll do that. Sine of 40 equals F parallel over the weight. Remember that red line is the weight, so it's 196. Cosine of 40 equals F perpendicular over 196. So if we calculate that real quick, the sine of 40 times 196 is 125.99. And that's going that way. And the cosine of 40 times 196 is 150.14. All right, so now we got to think a little logic again. We know it's moving this way. We know the force that's pushing the box down the hill is that force, the parallel component of the weight. What do we need to calculate before we go any further? The net force. To calculate the net force, we're going to go M times 8. So we got how much net force? 10 newtons of net force. And that's down the plane. So 125.99 newtons are pushing us down the plane. But to the box, it only seems like 10 newtons are pushing it down the plane. So how much friction is there? 115.99. And again, the way we calculated that is we know that the net force is equal to the parallel component of the weight minus the frictional force. So again, 115.99 is the frictional force. Sig figs, we just had 116. To calculate mu, using the Fun equation, mu is going to equal to the frictional force, 115.99, divided by what? The normal force, which is the perpendicular component of weight, so 150.14. Divide that out. We end up with 0.723 for mu. I'm going to stop that recording there real quick.